Hello and welcome to this lesson video where we will learn about machine power analysis using the performance charts published by the equipment manufacturers. This video covers the shown three learning objectives. The manufacturers publish for every equipment its specification sheet, which provides all important information about the equipment weight, dimension, and power. The equipment power is communicated using a performance chart that provides a full picture of the machine's ability to perform under different load and haul conditions. The performance chart is a graphical tool to identify the equipment speed and corresponding engine power for a specific haul job. There are three types of performance charts: Rimpull, Retarder, and Drawbar pull charts. Rimpull and Retarder are charts provided for wheel-mounted equipment like trucks, scrapers, and tractors. Drawbar pull charts are unique for track-mounted equipment like dozers. Let's study each one of these charts. Rimpull performance chart looks initially complicated and scary, but understanding them will be much easier by first checking their four axis lines. The top axis is for the equipment gross weight, which includes the equipment's own weight and the weight of the soil load if the equipment is in its whole trip from cut to fill, not the return trip from fill to cut. The right axis slope is equivalency shows the slope equivalency of the total resistance, which includes the grade and rolling resistance. As we covered in the last lesson, we can transform the rolling resistance from pound per ton or kilogram per ton to an equivalent grade slope, and then add it to the actual whole grade percentage to get the total resistance. This calculation needs to be done before using the performance chart. The left axis shows the Rimpull values that can be achieved over different engine transmission gears. The bottom axis shows the equipment speed values that can be achieved when the equipment runs on the different transmission gears. We can see the chart is for a scraper that has 8 transmission gears. You can easily relate to this chart if you drove a manual transmission car like me, or know how the power transmission system works. The gear performance curves form together inverse relationship between machine power and speed, which we covered in the last lesson. The highest the equipment speed, the lower the Rimpull it can provide. The first and second gears provide the highest Rimpull, but the slowest speed. The 8th gear provides the fastest speed, but the weakest Rimpull force. Now let's see how to use the Rimpull chart. First, you need to determine the machine weight to enter the chart from the top. The weight is expected to be between the empty and loaded dash lines. Sometimes the soil material is heavy and you will end up with a gross weight more than the average loaded weights provided by the equipment manufacturer. Let's follow here an example of an empty equipment traveling from the fill to cut, and it has an empty weight of 32,000 kilograms. You need to determine the second input value for the Rimpull chart, which is the total resistance. The total resistance is the addition of the grade and rolling resistance and represented in grade percentage values. The shown chart shows total resistance ranging from 2% to 30%. For our example, the equipment is driving uphill with 8% grade and experiences an additional rolling resistance equivalent grade of 7%. So the total resistance to overcome is 15%. Next, draw a vertical line from where the weight point marked on the top axis. The fourth step is to draw an inclined line from the total resistance marked on the right axis. Your total resistance line should be parallel to the shown inclined lines in the graph. Our goal is to find the intersection between the weight vertical line and the total resistance inclined line. From the intersection point, draw a horizontal line towards the gear curves to find the best engine gear to use for the implied weight and total resistance. Please note that I did not say draw a line to the left, but I said towards the gear curves. This is because in some cases your intersection point can be below the gear curves, which means you will draw a horizontal line to the right to intersect with the gear. So if we draw a horizontal line from the weight resistance intersection point towards the chart curve, we will hit the fifth gear. This means that the equipment will be able to move with the weight and overcome the total resistance by operating on the fifth gear. By knowing the gear operating points, we can draw a vertical line to the left to identify the exerted rimpull and draw a line downward to identify the feasible hole speed. For our example, we identify that the rimpull will be 4,800 kilograms and hole speed of 16 kilometers per hour. Our ultimate goal is to get the speed, but what is the benefit of knowing the rimpull force? The rimpull force is used in the last step to make sure that this is used fully and not more than the traction force. So that we will need to calculate the traction force as we did in the last lesson, and then find the usable force as the minimum of the rimpull and traction. If the traction force is more than the rimpull value from the chart, this means the whole surface is reliable, no tire slippage will happen, and the whole rimpull force will be fully usable. For example, if the traction force is found to be 6,000 kilograms, the usable force will equal the traction force. This means that you can use the speed from the chart, 16 km per hour, in your production calculations. But what happens if your whole road quality is bad and the traction force is low? If your traction force is low and controlling your usable power, you have two options. First, you can improve the whole road by installing whole road fabrics or dedicating graders and water trucks to maintain your whole road. You will need to do whatever is possible to bring the traction force up to at least the required rimpull force you found from the previous steps. The second option is to accept the bad hauling road quality and change your operation settings by using a lighter equipment or a different haul road with less total resistance. Let's explain this by reversing our previous steps and plug in a rimpull value that equals the controlling traction force. Let's say 3,800 kilograms. We can see that we can make two changes to your operation. We can continue using this whole road but reduce the whole load or even completely change the equipment. If we can keep the equipment but change the whole road to one with less rolling or grade resistance, so the total resistance is reduced to 8% instead of 15%. If any of these operational changes are done, you will end up with a speed of about 23 kilometers per hour. This means that you can end up with hauling less load but at a faster speed, which might be more productive than hauling more load at a lower speed or a slower speed. We will see such trade-offs when we cover the production rate calculations in future lessons. Now let's check the retarder charts. For safety reasons, heavy equipment is usually equipped with a device called retarder to automatically control the speed of the equipment when it starts gaining speed without a rimpull force from the engine. This happens when the equipment is driving downhill with a grade that's more than the rolling resistance. This means that this downhill negative grade will result in a total negative resistance, or we can call it assistance. In that case, the equipment operator does not have to push the gas or diesel pedal, and there is no resistance to overcome. I'm sure you experience that when driving on a downhill road. For such operation cases, we will need a different performance chart called Retarder Chart. It looks very similar to the Rimpull chart, but you can see we are missing the left Rimpull column, left Rimpull axis, as the engine is not really the one moving the equipment. You can also see that the effective total grade is now favorable, and these values are actually negative grades. Also, you can see that the power speed curves have that interesting sawtooth shape, where the vertical drops mark the points where the retarder device activates. We use the retarder chart similar to the Rimpull chart. We input the gross weight, loaded or empty, and the negative total resistance. Then we'll end up with only the speed, with no worries about the Rimpull value or slippage. You will just need to make sure that the speed you get from the retarder chart is not too high and exceed the safety speed limit imposed on the site. Done with two charts, let's check the last chart for drawbar pull. Drawbar pull chart is the performance chart for track-mounted equipment like track dozers. These look similar to the Rimpull chart but miss the weight top axis and total resistance right axis. This is because dozers do not haul and carry load, they push the load. For the total resistance, we will calculate it as a force and use the drawbar right axis values as our input entry. Left axis. For example, let's assume we calculate the total resistance to be 7,500 pounds. We enter the chart from the left with the drawbar pull equaling 7,500 pound and draw a horizontal line to the left. The horizontal line to the right to intersect with the gear powered speed curves. It will probably intersect with multiple gear curves, like here we intersect with all the gear curves. For this case, select the gear with the fastest speed so we can increase the production of the dozer. I hope you enjoyed this video and have now a clear understanding of the three main performance charts to determine the operating speed and the power of heavy equipment. Look for the exercises videos to see examples of the use of these charts. Thanks for watching and see you in another video.